Welcome to Terminal Velocity, the show where I optimize a problem until I wind up making it slower. Today is a big day because we're going to implement a novel optimization to Strassen's algorithm. Our past implementation of both recursive multiplication and Strassen's used a lot of memory in comparison to the textbook implementation, which only uses the memory from its argument. Using more memory generally hurts your chances of cache hits, and copying data is really slow to begin with. So despite our focus on speed, we have an interest in reducing wasteful uses of memory like this. So let's see what can be done. In all previous versions, our matrices were laid out in memory like this. The nth element of the array would be the nth element in the matrix if you read it like a book, top to bottom, left to right. This means the quadrants of the matrix are spread out all over the array, and we have to copy them into a temporary array where they're all together, repeating recursively until we reach our crossover point. What if we could just have an array that's always in the right order for Strassen's to consume it without any copying, regardless of what level of recursion we're on? That would let us spend 100% of the time in Strassen's flying through arithmetic. Thankfully, such a rearrangement exists. The best way I can describe it is that we're making little recursive Z-shapes out of the small matrices we saw via the textbook algorithm. It's probably better seen than heard. In this visual, I'm showing a rearranged 12 by 12 matrix. The numbers show what position in the array each element is rearranged to. Here, our crossover point is 6, so the smallest element in our Z-shape is a 6 by 6 matrix. This means the first 36 elements of our array are the 36 elements of the top left submatrix, then the top right, then the bottom left, then the bottom right. Now, let's rearrange that same matrix with a crossover point of 3. This time, our smallest element in the Z-shape is a 3 by 3 array. We follow the same pattern, and every time we make a square, we then recursively form a square made out of Z's on the top right, bottom left, and then bottom right, the same order as before, until we fill out the entire matrix. If we were to do this to a 24 by 24 matrix, this 12 by 12 matrix would just be the top left corner, flanked by 3 more 12 by 12 pieces of the same shape. This arrangement also lets us transform our input matrices once at the start, do as much multiplication, addition, and subtraction on them as we want while they're rearranged, and then convert the results back at the end, instead of having to convert to and from our special order in between operations. I'm only testing one multiplication here, but that's a very nice property to have for real-world use. Speaking of real-world use, this operation is only slightly more expensive than a standard memcopy and is actually very cache and vector friendly because, with a crossover size of 16, we can rearrange 16 contiguous elements at a time, which works really well with modern processor architectures. To illustrate this, let's see the Python code I used to develop this transformation. It's certainly not the prettiest code in the world, but the for loop in the base case has an array slice that copies a number of elements equal to our crossover size. This is actually a really elegant algorithm, and I was able to turn it into a very pretty piece of Lisp code, which I used to generate that visual of the rearrangement for this video. Of course, multiplying two transformed matrices will yield a transformed result, so we'll have to rearrange it with the inverse of that operation. The quickest working implementation I was able to produce isn't as elegant as the previous algorithm because it thinks linearly in terms of the rearranged matrix rather than the source matrix, so no fancy Lisp for this one. But just like the rearranger, the inverse operation copies 16 elements at a time, so it also exhibits the favorable cache and vectorization characteristics. My test cases are definitely the best case scenario for this optimization, but there are ways to use this technique on matrices of different shapes. We can stop rearranging the matrix at the point where a submatrix has an odd dimension, and then use the previous iteration of the algorithm at that point instead of our crossover point. Then cross over to the textbook implementation as usual at our crossover point. This switch will cause some thrashing in the instruction cache, but its impact should be very minimal since there's a very clear time delineation between the different algorithms used. There's also probably a reasonable way to do this, or something similar, on an odd-sized or non-square matrix, but I'll leave that as an exercise for the viewer. That was a lot to digest, so I'm going to save the actual C implementation and comparisons of performance characteristics for the next episode. The implementation especially has a lot to dig into. To make sure you don't miss it, smash that bell and keep it tuned to Code Points. Thanks for watching.